Okay, good morning to everyone. This is the seminar number 15 of the 2022 seminar series of the Magnetic Resonance Lab. And in this time, we have the honor of Rudolf Schäfer from Germany. So now I'm going to give pass to Carlos to do the introduction of our speaker. So Carlos, go ahead.
Well, thank you very much. I have the pleasure to introduce Rudolf Schäfer. He's professor. He got his PhD degrees in engineering, specializing in material science at the Erlangen University in 1990. After his postdoc stays at IBM Research in Yorktown and Forschungszentrum in Jülich, he worked. He moved to IFW, which is this Institute for Solid State and Materials Research in Dresden in 1993. He currently is the head of the Institute for Integrative Nanoscience. In 2011, he was appointed adjunct professor for the magnetic materials at the Technical University of Dresden. He became distinguished lecturer of the IEEE Magnetic Society in 2013, and I'll talk a little bit after I read this introduction about this year, 2013. And currently he chairs the Conference Executive Committee of the Society, of the Magnetic Society of the IEEE. His interest area spans from magnetic materials, with focus with magnetic and microstructures. He published over 200 technical articles in peer-reviewed journals, including books, chapters, and 2 monographs. And regarding these 2 monographs, I would like to say this. One of the monographs, he says, we have a different meaning for monografías in Spanish, which usually are essentially high school work, but his monographs include 2 books, essentially. I was called them Magnetic Domains and the Analysis of Magnetic Microstructure in 1998, of almost 700 pages, which we read a lot when we found striped domains in our thin films, and more recent work in magnetic microscopy of layers structures with other authors. So, and regarding the year 2013, I would like to say he was appointed, he was awarded the lecture award. He gave, he just told me, over 78 actually, invited talks all over the world. And at that time, we had the pleasure to have him in December 2013 giving us a talk in Bariloche. So thank you very much for being with us. Dr. Schäfer will talk about unconventional Kerr microscopy today. Thank you very much, Rudolf.
Thanks a lot, Carlos, for the kind introduction and, of course, for the kind invitation. It is actually a pleasure to be back in Bariloche, even though it's just virtual this time. But maybe times will be getting better in the future. Should I share my screen now?
Sure.
Yeah. Okay, you see my screen? You see my slides?
Not yet.
Not yet.
Not yet? Okay, I don't know what to do. Let me do it again. Share screen. Oh, okay, now I see. That was my mistake.
Yes.
Yeah.
It's okay.
So here we go. Okay, so my talk is about imaging of magnetic domains. And domains are areas in a magnetically ordered material, like in a ferromagnet, in which the vector field of magnetic moments is divided. So the photographs on the right show some examples of such patterns to give you an impression about the manifold of magnetic domains. You see that domains can be more or less complex depending on numerous parameters, but this is not the topic of today. The topic is rather about the method by which those images have been obtained, and that method is magneto-optical Kerr microscopy. A Kerr microscope is actually an optical polarization reflection microscope, as you can find it in any metallographic lab. To make it a Kerr microscope, the polarization microscope must typically be equipped with some electromagnet to magnetize the specimen. We furthermore need a polarizer to create linearly polarized light and an analyzer and compensator on the reflection path to detect the polarization state of the reflected light and to convert it into a domain contrast. Nowadays, LEDs are used as light source, and the domain contrast is enhanced by image processing so that a video camera is needed to bring the image to the computer. Besides Kerr microscopy, there are numerous methods for domain imaging, as they are listed here, which are sensitive to different parameters. To see this, remember that the magnetic flux or induction is actually the sum of magnetic field and magnetization, where the field may be an externally applied field and the stray field that emerges from a sample. So if the external field is equal to 0, Maxwell's equation saying that magnetic flux density must be divergence-free can be written as shown here, which immediately leads to this formula showing that any divergence in magnetization, which is actually equivalent to magnetic poles in the material, results in a magnetic stray field that emerges from those poles. So some of the imaging techniques are sensitive to the stray field, like the classical colloidal bitter technique or scanning probe techniques like magnetic force microscopy, Hall probe microscopy, modern nitrogen vacancy microscopy, or the indicator magneto-optical film microscopy. Transmission electron microscopy, like Lorentz microscopy, are sensitive to the flux density, and there are techniques that directly sense the magnetization vector. Magneto-optical microscopy, which is the topic of this talk, belongs to this class. Compared to methods that are based on X-ray dichroism effects or the use of spin-polarized electrons, and which requires synchrotron radiation, a very expensive and sophisticated equipment, a Kerr microscope is a rather inexpensive method, and it can be set up in any lab. So it's an in-lab technique. The method is nevertheless highly flexible in many aspects, and it can be applied to any kind of magnetic material. So it is not surprising that hundreds of conventional Kerr microscopes to exist around the globe in the meantime, so that Kerr microscopy may be seen as a well-established domain imaging technique nowadays. This talk, however, is not devoted to this established conventional kind of Kerr microscopy. It is rather about unconventional Kerr microscopy, or to express it differently, it's about surprising contrasts in Kerr microscopy. At least to me, using Kerr microscopy since decades as a tool to study magnetic domains, these are surprising findings in the sense that I wonder why nobody has obviously seen such contrasts, despite the mentioned fact that hundreds of Kerr microscopes are around in the meantime all over the globe, and that most of the effects which I will be talking about are known since a long time. The work is actually the result of collaborations with Ivan Soldato from IFW, who contributed experiments. He's a postdoc in my group, and with Peter Oppener from Uppsala University in Sweden, who helped with the interpretation. Peter also pointed out an effect which he had theoretically predicted some time ago, and which we indeed found experimentally in the course of this work. Later, I will call this the Oppener effect in my talk. Alexei Ognev and Alexander Smadak provided interesting thin film samples, and the presented results have recently been published in applied physical reviews. So for details, I refer to this article. For a better understanding why those contrast phenomena are surprising, let me briefly summarize the conventional understanding of Kerr microscopy. For the magneto-optical Kerr effect, a magnetic specimen is illuminated with plane or linearly polarized light, that is, with an electromagnetic field wave for which the electric field vector vibrates in a plane, which is created by some polarizer. Like all other material-specific optical properties, think of absorption, dispersion, or optical activity, or other effects, also the magneto-optical effects are dominated by gyroelectric terms, which means that they are described by the dielectric law D is equal epsilon times E. So here E is the electrical field vector of the incoming plane polarized light, and the dielectric displacement vector D describes the E field within the material. And this dielectric constant epsilon is actually a tensor. Now let us assume we have a non-magnetic specimen in which also any other kind of optical activity shall be absent. So we have an optically isotropic material. Then the dielectric tensor only contains the diagonal elements that are equal to 1. All other elements are 0. The displacement vector would then be along the same direction as the incoming E vector of the incident light. And therefore the reflected light will be polarized along the same plane as the incoming light. The light would consequently interact with the matter without rotation of its plane. Rotation and ellipticity of the outcoming light requires non-zero off-diagonal elements in this tensor. And this is the case if the specimen is magnetic with some magnetization vector. These off-diagonal elements, in case of a magnetic sample, contain the direction cosines of the magnetization vector M along the 3 spatial directions and the so-called Vogt or void constant QV, which is a frequency-dependent complex material parameter. It is roughly proportional to the saturation magnetization, and it describes the strength of the Kerr effect. So after interacting with the magnetization of the specimen, and according to those off-diagonal elements in the tensor, the reflected light now consists of 2 components. A normally reflected component, shown here in gray, that is polarized along the same plane as the incoming light, and a much smaller Kerr component that is polarized perpendicular to the normal component. Here in this sketch, the Kerr amplitude is actually shown heavily exaggerated for display purposes. Both components are in general phase shifted so that the reflected light is rotated and elliptically polarized. If there would be no phase shift between N and K, there would be only a Kerr rotation and no ellipticity. So to summarize this, if there would be 2 oppositely magnetized domains in the material, the incoming plane polarized light would be reflected as rotated elliptically polarized light with a rotation and the sense of ellipticity depending on the magnetization direction. A very convenient way to describe the Kerr effect, especially its contrast symmetry, is based on the classical Lorentz concept. To see this, we can write the dielectric law of the Kerr effect in this mathematically equivalent form. And this cross product M cross E points to a Lorentz force perpendicular to the magnetization vector and the E vector of the incoming light. And the direction of this Lorentz force M cross E may be seen as the Kerr vector. This is illustrated here in more detail. According to this Lorentz concept, the E vector of the incoming light is assumed to cause a vibrational motion of the electrons in the material along the direction of the E vector, which in this case means along the plane of incidence. The magnetization vector M then causes a Lorentz force that acts on these vibrating electrons, leading to rotation of the vibration plane and thus also to rotation of the reflected light which is actually emitted from those vibrating electrons. And for the given E vector and M vectors in this case here, which actually corresponds to the sketch here on the left side, the Lorentz force M cross E and thus the Kerr vector points towards us. So by vector addition with N and K, this leads to the Kerr rotation. And based on this very simple Lorentz concept, 3 basic Kerr configurations can be derived, which are illustrated here by ignoring ellipticity for simplicity. So only rotation is shown. In the polar configuration, the magnetization is perpendicular to the surface, and the effect would be strongest at perpendicular incidence. In the longitudinal configurations, the M vector is in plane and along the plane of incidence. So here a Lorentz force occurs for both light being polarized along and transverse to the plane of incidence, called P and S polarization. If the M vector, and all these cases, there's a Kerr rotation of the reflected light, as K is always perpendicular to N. So longitudinal Kerr effects with P and S polarized light always lead to a Kerr rotation. If now the M vector is transverse to the plane of incidence and the incoming light is P polarized, there's also a Lorentz force and thus a Kerr component, which however now is polarized along the same plane as the reflected E vector. So in this case of the transverse Kerr effect, there is no Kerr rotation, but rather an intensity modulation of the reflected light. So please keep this in mind. I have to come back to that later. Another classical but more microscopic interpretation of the Kerr effect is based on the Fresnel concept. So accordingly, the Kerr effect may be primarily seen as a circular birefringence effect that is possibly superimposed by some circular dichroism. So this concept is based on circularly polarized light. And a circular polarized wave consists of two orthogonally polarized plane waves of equal amplitude that are phase shifted by 90 degrees. And this can result in right or left-handed circular light depending on the direction of this phase shift. Now, why is the Kerr effect called magnetic circular birefringence? To see this, we have to be aware that a plane polarized wave can actually be seen as being generated by the superposition of two circular waves with equal amplitude and opposite handedness, as is also illustrated here in this video. Now assume that we have a magnetic specimen with perpendicularly magnetized domains and perpendicular incidence of light. So these are the conditions for the polar Kerr effect. When the two circular partial waves now enter the material, they will feel different refraction indices that depend on the magnetization direction. And in general, a material that is placed to different indices of refraction is said to be birefringent. So these two partial waves now enter the material, they have different velocities, and by leaving the material, they will be phase shifted. And this phase shift can be positive or negative, depending on the magnetization direction of the domains. The superposition of such phase shifted circular waves then leads to a clock or counterclockwise rotated plane polarized wave for these two domains, which is also illustrated here in this lower video here. You see the superposition of the red and green phase shifted circular waves resulting in a rotated linear wave. One of these two plane waves can now be blocked by an analyzer. In this case, it's the upper domain here, the light from the upper domain, so that the upper domain will appear dark, and with the same analyzer setting, the light of the lower domain can pass the analyzer so that the lower domain will appear bright. So there will be a domain contrast generated by the analyzer. Without analyzer, we wouldn't get a domain contrast. Now, if now, in addition to this phase shift, there's also different damping of the two circular partial waves, we will have also circular dichroism. The superposition of differently damped and phase shifted circular partial waves will lead to rotated, elliptically polarized light. The two waves are actually differently damped for the two magnetization directions, so that we get oppositely rotated waves of opposite ellipticity for these two domains, as it's schematically shown here. Now, to generate a domain contrast, it is helpful to use a so-called compensator. A compensator is, for instance, a quarter wave plate, and it acts like a phase shifter. To illustrate this, remember that reflected elliptically polarized light may be seen as being composed of two phase shifted plane waves, as illustrated here. And by properly rotating now the compensator with some fast axis, the phase of these two partial waves can be adjusted, and when they are in phase, we get a linearly polarized wave, which can be blocked by the analyzer. So in our case of our example, if the fast axis of the compensator is turned perpendicular to the Kerr rotation of one of these ellipses, we will get a plane wave that is rotated now by the Kerr angle plus the ellipticity angle. For the same compensator setting and the lower domain here, the ellipticity is enhanced. And again, we can use an analyzer, block the light, let's say, of the upper domain. This will appear dark, and with the same analyzer setting, this elliptical light from the lower domain will pass so that this domain will appear bright. So the essential point is of this diagram that we have seen that magnetic circular dichroism, the size different, which means different damping of left and right circular light, is normally superimposed to some circular birefringence, leading to this rotated ellipses in the most general case. So here an obvious question comes to mind. And this question is, can also the pure magnetic circular dichroism, in short the MCD effect, be observed and possibly be used for domain imaging? For X-ray imaging, this is well established, as you know, based on the XMCD effect. But for visible light, nothing much has been reported on this possibility so far. In order to make use of the MCD effect, the sample needs to be illuminated by circular light of one rotation sense. If there would be two rotation senses, like in the upper case, there would always be birefringence superimposed. But using circular light of just one rotation sense, this can be either left or right-handed, the wave will be differently damped in dependence on the magnetization direction and caused by the MCD effect. So the light should be reflected with different intensity from the two domains, which should readily lead to a domain contrast without the need of any analyzer or compensator. That is, without any polarization analysis. In a few minutes, I will show that this is indeed possible also by using visible light, not just X-ray light. This brings me finally to the topic of my talk, which is unconventional Kerr microscopy, or to be more precise, let us call it analyser-free, intensity-based Kerr microscopy. As for such intensity modulation effects, an analyzer would be useless. An analyzer and possibly a compensator would only be useful if there would be some Kerr rotation, but not for intensity modulation effects. Making use of this MCD effect is just one possibility for intensity-based microscopy. Another possibility, which I have mentioned already, is the transverse Kerr effect. Here the Kerr component is along the normally reflected light component, so there's no rotation, but rather an intensity modulation that depends on the direction of the transverse magnetization. So this should also lead to domain contrast without an analyzer, as there's no rotation involved. The third possibility is the mentioned effect that was predicted by Peter Oppenauer, and that was never experimentally considered or observed so far. And finally, also linear dichroism effect can be used for analyzer-free domain imaging. So in the following, I will address all these four effects. Let me start with the transverse Kerr effect. This effect requires in-plane magnetized material and the magnetization component transverse to the plane of incidence. So experimentally, we need to define the plane of incidence. Let me briefly make a little excursion to the setup of our Kerr microscope in order to show you how the light incidence is adjusted experimentally in our case. So our Kerr microscope is a wide field optical polarization microscope in which the light of LEDs, which are sitting in some controller, is guided to the lamp house of the microscope by fiber optics. And the ends of these fibers are sitting somewhere in the lamp house. They can be seen by looking at the back focal plane of the microscope, which is possible by simply taking out the ocular and looking into the so-called tube of the microscope. This is this back focal plane where you see the ends of the glass fibers. Now, let us assume we have 4 such LEDs, with the glass fiber ends being acentrically located as indicated here. If we switch on now the upper LED, which is also shown here from the side view, so we switch on the upper LED here, and follow the ray path through the microscope, it is obvious that you have oblique incidence from the right in this case. Activating the opposite LED, the lower one, shown here also in the side view, which is the deep blue one, and again, following the ray path, you see there's oblique incidence from the left. If both LEDs are on at the same time, we get oblique incidence from left and right at the same time, which leads to an effective perpendicular incidence. So this would be polar sensitivity. Accordingly, by activating the horizontal LEDs, there would be incidence from the front and from the back. And this can all be done by computer control. The diagram here on the right shows how the LEDs are defined in the remainder of my talk, as seen from the top of the microscope. So we are looking down from the camera through the reflectors, through the objective lens down to the sample. And this is the view here shown on the right. LEDs 1 and LED 3 define planes of incidence transverse to the microscope axis, while the plane would be along the microscope axis for LEDs 2 and LED 4. And the sketch in the middle shows this reflector, which is actually sitting here in the microscope and which is a semi-permeable mirror that reflects the light down to the objective lens where it's reflected, and it passes the mirror again and goes towards the camera. And this is demonstrated here for the example of LED 1, which is this left LED here. So when the LED 1 is on, it enters this mirror and the objective lens from the left, leading overall to a horizontally or transverse plane of incidence, transverse to the microscope axis. Switching on LED 2, this would be this one here, would lead to a longitudinal plane of incidence. But now back to the transverse Kerr effect. To demonstrate this effect, we have used an iron silicon sample, electrical steel sheet with a 100 surface. So there are two easy axes of anisotropy within the surface as indicated here. And this is important because we need in-plane magnetized material to see some transverse Kerr effect. And this sheet sample has a diameter of 10 millimeters, and it is placed between the poles of a quadrupole magnet that allows to rotate the magnetic field continuously by 360 degrees. In our case, we have used red LED light because this gave us the strongest contrast. So now here it is demonstrated that the transverse Kerr effect can indeed be applied for domain imaging. The first three images here have been obtained without analyzer and the proper conditions of the transverse Kerr effect. That means oblique incidence of light and polarization along the incidence plane. So on the left two images here, we see a domain contrast for horizontal planes of incidence by activating LED 1 and LED 3. And in fact, we see a maximum domain contrast between these vertically aligned domains because they are transverse to the plane of incidence. So this is pure transverse sensitivity because for the domains magnetized along the plane of incidence, there is no contrast. If we switch the direction of incidence, so instead of LED 1, we switch on LED 3, then you see that this transverse effect of this transverse domain changes, the contrast changes sign, so white becomes black and black becomes white. And again, there is no longitudinal contrast. There's only transverse contrast. For a vertical plane of incidence and polarize again along this plane, the transverse Kerr effect now causes a contrast between the horizontal domains, which are now the transverse domains, while the vertical domains remain without contrast. And with the same plane of incidence, but now the polarizer perpendicular to the plane of incidence, the conditions of the transverse Kerr effect are abundant, because for the transverse Kerr effect, we always need p-polarized light. This would actually be the conditions for the longitudinal Kerr effect with S-polarization, which, however, cannot be observed as it is a rotation effect requiring an analyzer. And all these images have been obtained without analyzer. In fact, without analyzer, we rather observe a contrast that is quadratic in the magnetization. So here all domains along the same axis show up in the same color, while a contrast is observed for domains magnetized along orthogonal axes. All these features can also be verified in those sensitivity curves. To measure these curves, a magnetic field was applied that saturates the sample, and then the field was rotated by 360 degrees, and the Kerr intensity was plotted as a function of field, which means magnetization direction. So what we get actually are curves in which the Kerr contrast is plotted as a function of the magnetization angle, and this we call sensitivity curves. Under our two transverse conditions with horizontal and vertical plane of incidence, here shown in the red, by red and black curves, we see that the sensitivity curves follow a sine and cosine dependency, as it is to be expected according to these domain images. The red curve, for instance, corresponds to the left domain image here. We see that for phi equals 0 and 90 degree, there is zero contrast, as can also be seen here in the domain image. While for phi equal 90 degrees and 207 degrees, there's maximum contrast, as also seen in the vertical domains here in this image. Under conditions of the right image, which is actually the blue curve in this plot, we see a sine 2 phi curve in accordance with this quadratic contrast seen in the right image. I will return to that contrast later. It is caused by the mentioned linear dichroism effect. Two remarks. First of all, we are not aware that the transverse Kerr effect has ever been applied for imaging in a wide field magneto-optical Kerr microscope, although it leads to a very high contrast, as you have seen before in these images. So this is a bit surprising why nobody has tried that out so far. It was applied, however, to obtain domain images in a so-called laser scanning Kerr microscope back in 1993 already. In such a microscope, a domain image is created by a laser beam, like in a Moog magnetometer, that is then scanned across the surface to build up the image sequentially. This is the only explicit application of the transverse Kerr effect which we found in the literature so far. And secondly, even if the transverse Kerr effect is not applied intentionally, it can have an influence on conventional analyzer-based imaging using the longitudinal Kerr effect. Remember that the longitudinal Kerr effect can be measured for both light being polarized perpendicular and parallel to the plane of incidence. Parallel and perpendicular to the plane of incidence. Parallel polarization, however, is also the condition for the transverse Kerr effect. So when we perform conventional longitudinal Kerr microscopy, which requires contrast formation with an analyzer, we can in fact see some transverse domain contrast in addition to the dominating longitudinal contrast. And this is shown here in this picture here. No? So there's horizontal plane of incidence activating LED 3. If this would be pure longitudinal effect, there should only be a longitudinal contrast, but you see that the superimposed transverse Kerr effect. If the polarizer is along the plane of incidence. If, however, the polarizer is perpendicular to the plane of incidence, we only have as polarized longitudinal Kerr effect. There's no transverse Kerr effect possible. And in fact, you see that the transverse domains do not show any contrast. There's only a dominating longitudinal contrast. And this can also be seen here in the sensitivity curves. For p-polarized light, which is here the upper case with LED 3, and polarizer horizontally along the plane of incidence, there's a significant phase shift when you compare these measured black dots here with an assumed pure longitudinal curve. And this phase shift indicates the presence of some superimposed transverse Kerr effect. While using S-polarized light, which is the red curve, there is no phase shift. There's pure longitudinal sensitivity. You see some slight distortions of the measured plots from the ideal sine curve, and this is due to some superimposed quadratic effects which cannot be avoided. So much about the transverse Kerr effect. Now let me address the Oppenheimer effect. This effect, which may actually be seen as a 45-degree dichroism effect, was predicted by Peter Oppenheimer back in the year 2003, but for X-ray frequencies. It is expected to exist also in longitudinal and polar geometries. And here in this paper, which I've mentioned, and also in this talk, I will show you that this effect can also be used for domain imaging in visible light. So far, it was not even been proven for X-rays, but we have proven the existence of this effect for the first time using visible light. The open-air effect requires polarization at an angle, best at 45 degrees to the plane of incidence. So this is different to the conventional longitudinal and transverse Kerr effects, where the light is polarized parallel or perpendicular to the plane of incidence. And the contrast phenomenology of the longitudinal open-air effect is visualized here by applying the Lorentz concept again. So the magnetisation is assumed to be along the plane of incidence, and the polarizer setting of 45 degrees is assumed. So there are S and P polarized components of the incoming light and of the reflected light. Those S and P components are responsible for the indicated Ks and Kp components on the reflection paths that can be derived based on the Lorentz force. And by vector addition of these Kerr components with a normally reflected light shown here in gray, this results in a shortening of the normally reflected light. If the magnetisation is inverted, now it points to the left, and by again adding those Kerr vectors to the normally reflected light, we see it results in an extension of the normally reflected light. So there's a dimming and an increase of intensity when the light is reflected from those antiparallel domains, so we can expect a domain contrast without the need of any analyzer. As shown on the left here, keeping the magnetisation vector along the same direction, but rotating the light from +45 to -45 degrees also leads to a shortening and an extension of the reflected component. So there's also a contrast change when we rotate the polarizer by 90 degrees from +45 to -45 degrees. Also note that when the magnetisation is not strictly along the plane of incidence, but if it's rotated, so that there is also some magnetisation component transverse to the plane of incidence, then the p-polarized component of the incoming light should also cause some transverse Kerr effect that should be superimposed to this longitudinal open-air effect. In other words, for arbitrary magnetisation direction, there will be always a superposition of this longitudinal dichroic contrast and the transverse Kerr effect. And this can now be verified experimentally. For a given polarizer setting of -45 degrees and light coming in from LED 1, from the left, we indeed see some longitudinal and some transverse domain contrast. When the light comes in from LED 3 along the same plane, you see that both the longitudinal and the transverse contrasts are inverted compared to the case with LED 1. Turning now the polarizer from -45 to +45 degree leads to an inversion of the longitudinal contrast, but not of the transverse contrast. Just compare the upper and the lower images. Furthermore, note that both domains magnetized along and transverse to the plane of incidence show comparable contrasts in all these 4 images. This indicates that the longitudinal open-air effect and the regular transverse Kerr effect are about of equal strength. And this can also be verified now by the sensitivity curves again. Those curves have maxima and minima at 45 degrees, 135, 225, and 350 degrees, different to pure transverse or pure longitudinal curves, which always have maxima minima at 0 and 90 and so on. This indicates that longitudinal and transverse contrasts are about of equal strength. And turning the polarizer now to +45 degrees, this leads to sensitivity curves with the same symmetry, but which are now shifted in phase by 90 degrees compared to the other case. Besides the longitudinal configuration, the open-air effect can also exist as a polar effect, which was also predicted by Peter Oppenair back in 2003 already. And this is demonstrated here for an ultra-thin cobalt iron boron film with just 0.9 nanometer thickness and with perpendicular anisotropy. Turning the polarizer from plus to -45 degrees leads to an inversion of the contrast, as seen in these 2 images. On the left side, you see for comparison the same domain state, but now imaged by conventional polar Kerr microscopy using an analyzer. So this open effect leads to equal strength of contrast images like conventionally. So much about the open air effect. Now let me address the magnetic circular dichroism, or MCD effect. As already shown, an MCD contrast should be seen when a sample is illuminated with circularly polarized light of a given helicity, which is then differently damped for different magnetization directions, leading to a domain contrast without the need of an analyzer. Circularly polarized light is generated by using a linear polarizer, followed by a quarter wave plate. And if the fast axis of this quarter wave plate is at 45 degrees to the polarization axis, we get circularly polarized light. As after the quarter wave plate, what we get is two orthogonally polarized partial waves that are linearly polarized, but phase shifted by 90 degrees. And this leads to a circularly polarized wave. And by rotating the polarized by 90 degrees, we can switch from right to left circularly polarized light. So this is how we create the circular polarized light in our microscope. This is very easy. And we found that the MCD effect can indeed now be used for domain imaging in both polar as well as longitudinal geometries. Here, two images using the polar MCD effect are shown. The sample was again this ultrathin cobalt iron boron film with perpendicular anisotropy. In fact, we see a strong domain contrast in circular light, and changing the helicity from left to right-handed, we see that the contrast is inverted as expected. As mentioned, the MCD effect also leads to a contrast in longitudinal geometry. That means at oblique incidence of light on in-plane magnetized material. And this is shown here again for our iron silicon sample and oblique illumination along the vertical plane in all these four images. First of all, we note there's indeed a longitudinal domain contrast, a contrast between the domains magnetized along the plane of incidence in all these four images. And this contrast is inverted when the direction of incidence is inverted. Simply compare the other two images here, where we have LED2 and LED4, so the longitudinal contrast is inverted. Comparing now the upper and the lower images, we see that inverting the helicity from left to right-handed leads to an inversion of this longitudinal contrast. And in all images, there's also a contrast between the transverse domains. This indicates the simultaneous presence of longitudinal and transverse Kerr sensitivity. And this transverse contrast does not depend on the handedness of the circular light. It has the same sign for both helicities. Just compare the upper and lower images, indicating that this intensity contrast is caused by the transverse Kerr effect that must be generated by the p-polarized component of the circular light. Any circular light, of course, always has a p-polarized component, and this is responsible for transverse Kerr effect. The domains transverse to the plane of incidence show a somewhat stronger contrast than those magnetized along the plane of incidence, indicating that the transverse Kerr effect is a bit stronger than the longitudinal MCD effect. And these effects can now again be seen in the sensitivity curves. If there would be pure transverse sensitivity, we would measure the black curves here for different LEDs. The obtained curves, however, are shifted, phase shifted, indicating the superposition of this longitudinal MCD effect onto the transverse Kerr effect. And this phase shift is less than 45 degrees, indicating that the transverse contrast is stronger than the MCD effect. Again, some remarks concerning these MCD observations in the literature. The MCD effect using left and right circular light rather than linear polarized light was recently applied to image domains in a platinum cobalt multilayer film. Although the authors talk about magneto-optical Kerr effect microscopy, what they have done actually is Faraday microscopy. So Faraday microscopy means the same as Kerr microscopy, but in transmission. As in their geometry, what they had was the magnetic film, and on the bottom there was an aluminum film. So the light entered the magnetic film, passed it, it went through the silicon oxide, which is transparent, and then it was reflected for the aluminum. So this is effective transmission microscopy, but in reflection geometry. So you should not talk about Kerr microscopy. In that case, it was Faraday microscopy. And the authors furthermore claimed that the MCD contrast was only possible by embedding the magnetic film in these silicon oxide films, which are dielectric anti-reflection layers. Note that in our case, the images I've shown you before on this cobalt iron boron film were obtained without anti-reflection layers. And they were obtained in true Kerr geometry because there was no mirror layer underneath. So my claim is that we have been the first that have really seen true MCD effect in Kerr geometry. And secondly, domain imaging uses circular light was already reported back in 1975 by Kulow and Lambeck on bulk chromium bromide material, which is nowadays very prominent again as a novel 2D material. Again, this was Faraday microscopy rather than Kerr microscopy. For imaging, they actually have used the transmission polarization microscope. So to our best knowledge, this is the first application of MCD-based imaging using visible light. In this case, it was blue light. It was forgotten for more than 30 years. So much about the MCD effect. Now let me finally address the magnetic linear dichroism or MLD effect, which leads to a contrast that is quadratic in the magnetization. Therefore, 180-degree domains show the same color, and there's only a contrast between 90-degree domains. This effect is actually related to the classical Vogt or Voigt effect. So we better talk about Vogt microscopy. Here the term linear refers to the fact that linearly polarized light is used for illumination. The magnetization vector must now be in plane, and the light is supposed to propagate perpendicular to the magnetization vector, best at perpendicular incidence. Under these conditions, a Kerr effect would not be possible, as the Kerr effect always requires a magnetization component along the propagation direction, as we have seen before. Now, if the light propagates transverse to the magnetization vector, the eigenmodes are not circular waves, but rather linearly polarized waves, with vibration planes along and transverse to the magnetization vector. Both components proceed in the medium with different damping. Here in this sketch, we assume that the domains transverse to the polarization direction have a stronger damping than those longitudinal domains. This thus leads to a domain contrast between the vertical and the horizontal domains. Turning the polarizer by 90 degrees now leads to the same effect, but now the vertical domains, which are now the transverse domains, have a stronger absorption, so we get an inversion of the contrast. And these images here demonstrate that this quadratic contrast and its inversion when turning the polarizer by 90 degrees in fact exists. At a polarizer setting of 45 degrees, the domain contrast disappears, as now the two orthogonal easy axes absorb the light equally. The most remarkable point here is that without analyzer and compensator, a quadratic Vogt contrast is seen when the incoming light is polarized along or perpendicular to the magnetization axis, which is the case in these two images here. While at 45 degrees, there is no domain contrast. And this is now a bit surprising because it is different to classical conventional Vogt microscopy, as demonstrated here on the right again for the case of iron. Under classical or regular conditions, the Vogt contrast is generated again at perpendicular incidence, but now by using analyzer and compensator. We see the same quadratic domain contrast as without analyzer and compensator, but now the light must be polarized at 45 degrees, where in the case without analyzer, no contrast was seen. To understand that difference, let us go a bit deeper into the physical mechanisms of the Vogt effect. We have seen that the Kerr effect is described by the dielectric tensor that can be interpreted in terms of this Lorentz force as shown before. And we have also seen that according to this tensor, oblique incidence of light is required to get a domain contrast of such in-plane magnetized domains that is linear in the magnetization. The Vogt effect is normally described by its own dielectric tensor, in which the magnetization enters quadratically as expected and with its own material constant. It can be shown, however, that this tensor is actually not needed, as the Vogt effect can as well be explained on basis of the gyroelectric law, which means by using the Lorentz concept like for the Kerr effect. So both Kerr and Vogt effect can be explained by the same tensor. And this is illustrated here for a lambda pattern consisting of 4 domain phases as indicated here. So there's a flux closed magnetization configuration. Let us assume that X polarized light is propagating along the Z direction. So we have perpendicular incidence of X polarized light. This EX component generates a 0 order displacement dx equal to epsilon times EX in the material. So this dx vector is parallel to the EX vector. This is the 0 order displacement. According to this gyroelectric tensor, the EX field now will not cause any Lorentz motion in this horizontal X domains here, because here the cross product M cross E is equal to 0. So in the two X domains, there's only the X displacement, but not the Y displacement. There's no rotation of light in the X domains. In the two vertical Y domains, however, Lorentz motion along the plus minus Z direction are induced now, according to the Lorentz concept, leading to this first order displacement dz equal to I times epsilon times Q times My times Mx. This term actually is simply the lower left term here in the tensor, which connects the dz with the Ax component, according to this law here. Those first order displacements now cause a first order depolarizing field Az, which is opposite to dz, just to keep dz equal to 0. And this depolarizing field Ez now induces a second order displacement dx dash equal to I times epsilon times Q times My now. This term simply corresponds to the upper right term in the tensor here, which connects dx with Az. By replacing now this Ez with this first order depolarizing field here in the upper equation, we see that the x dash is in fact now proportional to My squared. So this is a quadratic dependency on the magnetization vector. In the sketch here, we see this quadratic Tx dash vector points to the left for both Y domains. It is thus opposite to the 0 order displacement dx. There is no dy component in the two Y domains, so there's no rotation of light. There's only amplitude modulation. As the second order displacement is opposite to the first order displacement or 0 order displacement, the amplitude of these two Y domains is now reduced, and we get a domain contrast between the Y and the X domains, which is quadratic in the magnetization vector. And this is exactly the situation we have seen before. So this is pure linear magnetic dichroism. The classical Vogt effect, which is obtained at light polarized at 45 degrees to the magnetization directions and requiring analyzing compensator, as seen before, can be understood along the same line. Assume now we have again incidence, perpendicular incidence, and polarization along X, but now the sample rotated by 45 degrees. We can now again derive first and second order displacements. So we see that now that Lorentz motions are excited in all four domains, leading to the X dash components along minus X in all these four domains, pointing to the left. And we have the Y components of opposite sign for neighboring domains. Just compare these two domains or these two domains. And these dy components are now responsible for antiparallel EY components in the reflected light, which are phase shifted by 180 degrees. Now, when the phase of one of the two EY vectors is matched with that of EX by means of a compensator, a black and white microscopic contrast is generated in neighboring domains if the analyzer is perpendicular to the polarizer. So I know this is a bit complicated, but anyway, the message is that conventionally a Vogt contrast requires analyzer and compensator and a 45-degree polarization, while this pure MCD effect, which I have shown before, occurs without analyzer and compensator, and the light must be polarized along the plane of incidence, along the magnetization vectors. And the final remark, so I'm really getting close to my end now. In all these images, there's also always a domain boundary contrast visible. And this domain boundary contrast, seen here as black and white contrast, or here also black and white contrast, is caused by the magneto-optical gradient effect, which follows a certain dialectic law in which the magnetization gradients enter this tensor. And this effect shows up as a domain boundary contrast. As across domain walls, the magnetization gradients are strongest. And this boundary contrast, of course, alternates from boundary to boundary. Like the Vogt effect, also the gradient effect can be observed conventionally by using analyzer and compensator, as shown here on the right. But by comparing the images, it is evident that conventionally at a polarizer setting of 45 degrees, the 180-degree domain boundaries show up as with a black and white contrast. While for polarizer settings along the EZ axis, the upper image here, the 90-degree boundaries show up. In the analyzer-free mode, however, this is opposite. Here, the 180-degree domain walls show up when the polarizer is along the walls. And at 45-degree settings, both 180-degree and 90-degree walls show a contrast. And this difference can be explained by the fact that conventionally, in the conventional gradient effect, it is caused by these off-diagonal elements in the tensor, and the analyzer compensator free mode is due to the diagonal elements. I don't want to go into further detail about that. Let me summarize. Various possibilities of intensity-based Kerr microscopy, that means methods that do not require analyzer and compensator compared to conventional microscopy, have been demonstrated, which obviously have not been considered or have been overlooked in the past. There's the transverse Kerr effect, which uses linearly polarized light for illumination. This effect can be used on in-plane magnetized material with sensitivity curves that are much more accurate than those of conventional longitudinal Kerr microscopy. This effect should therefore be considered for quantitative Kerr microscopy, where the precise adjustment of sensitivity is mandatory to calibrate the contrast. Also, the Oppenheimer effect requires linearly polarized illumination. It is a 45-degree dichroic effect, meaning that the light needs to be polarized at 45 degrees to the plane of incidence. It may be superimposed by a transverse Kerr contrast of similar strength, leading to 45-degree phase-shifted sensitivity curves. The magnetic circular dichroism or MCD effect requires circularly polarized illumination. It exists in polar and longitudinal geometry, where in the latter case, the MCD effect is superimposed by a stronger transverse Kerr effect. And the magnetic linear dichroism effect requires linearly polarized illumination. The effect is quadratic in the magnetization, and it is strongest at perpendicular incidence on in-plane magnetized materials. A remark: the magnitude and obtainable contrast is just about 15% of the conventional analyzer-based Kerr contrasts in each case. But enhanced by image processing, the domain contrast is as strong as by conventional Kerr microscopy. This was obvious from all the iron silicon images I've shown before, and also from the images of the polar media, which were actually processed by background subtraction. And a final remark now: domains can be imaged without polarizer. This is demonstrated here for the iron silicon sample again. So in this case here, we have removed analyzer, compensator, and polarizer from the microscope. So it's not a polarization microscope anymore. Nevertheless, we get a strong domain contrast. Interestingly, using unpolarized light obviously leads to transverse domain contrast, which can easily be verified when you observe these images. For instance, here LED1, horizontal plane of incidence, there's a domain between the contrast between the transverse domains. So it seems that when you use unpolarized light, there's of course always a p-polarized component, and this always causes a transverse Kerr effect. So now I'm at the end. I think I've spoken a bit longer than expected, so thanks for your patience. And I'm happy to answer any questions that you have.
Good. Thank you. Thank you, Rudolf, for your amazing talk. Most of the people is clapping in the conference room, but there is no microphone. So now I would like to open the session to question. If you have any question, you can raise your virtual hand or write the question in the chat box. So if anyone wants to start, or I can start if you want. Okay, I will start. When you perform the angular dependence of the intensity, I suppose you apply a small field only to rotate the magnetization.
No, it must be a strong field, because you have to saturate the sample. so that the magnetization follows the field, and then you turn the field around by 360 degrees. So the field must be stronger than the anisotropy field of the specimen in order to guarantee that the sample is saturated.
Okay, but why do you have domains if you are saturated? This is a closure domain.
No, this is only for the sensitivity curves to saturate the sample. Otherwise, all domain images you have seen have been obtained at zero field.
Okay, I understand now. Yeah. And at some point, you said that the transversal and the longitudinal intensities should be the same. I think this is a very simple question, but it's still not so clear for me. In the angular you mentioned that the transversal signal and the longitudinal signal, the amplitude should be the same.
This applies only to the open-air effect. So normally, when you look at this, let me go back to one of the sketches here. So in that sketch here, we see that the longitudinal effect always is a rotation effect. So this can be maximized by using compensator and analyzer to give you some maximum contrast. The transverse Kerr effect cannot be optimized with analyzer and compensator because it's an intensity effect. So it's in the best case superimposed to that effect, but much weaker. In order to observe the transverse Kerr effect in the pure mode, we have to take out the analyzer and do some image processing to get images as you have seen them before with the same contrast level. And as mentioned, the contrast here in this pure transverse geometry without analyzer is only about 15% of that you can obtain by using analyzer and compensator in the longitudinal classical geometry. So the transverse Kerr effect is always much lower, weaker in contrast. The fact that you get equal contrasts for both longitudinal and transverse components only applies to the open-air effect.
Okay.
Where you have this 45-degree polarization.
Okay, thanks. It's clear. It's more clear for me now. Anyone else? I think Carlos has a question. He opened his microphone.
Thank you very much, Rudolf, for your very didactic talk. Thank you very much for that. I don't know if I understood all that you mentioned because I'm not a specialist in magneto-optics.
Yeah.
But you mentioned that the X-ray magnetic circular studies that are done in cyclotrons had a relation with the talk that you mentioned. The opener effect is different from what the X-ray magnetic circular diffraction is talking about.
For the opener effect, yeah, okay, go ahead.
And can the opener effect open something new on magnetic circular studies on X-ray?
Well, actually, this was the prediction of Oppenheimer when he wrote this paper. So this Oppenheimer is a theorist. So he predicted this by theory, but to my understanding, this has never been tried experimentally because you have to use linear polarized X-ray light at 45 degrees. So there's no publication that has tried that out.
I see.
Okay. But it should be possible easily. Yeah? One should simply try it. Now we know that the effect exists, in fact, for visible light, so there's no reason why it shouldn't exist at X-ray frequencies.
At X-ray frequencies, okay. Well, your presentation was very clear for the people that are specialized in the subject, I can imagine. Thank you very much, Rudolf, again.
I have another question, Rudolf. I read some recent papers on time-resolved mode microscopy. Can you do some comment about that?
Yeah, I mean, this is possible. But the point is that if we use a wide field optical polarization microscope, as we do, and to do time resolution at a very high speed, high dynamics in the, let's say, a gigahertz range, then you need to use a laser, which is pulsed as for the pump probe measurement. And lasers are, of course, coherent light sources. And in an optical polarization microscope, a laser always causes interference speckle. So any dust particle in the objective lenses or in the lenses of the microscope lead to a strong speckle contrast by diffraction that is usually much stronger than any domain contrast. So what you need to do is you have to destroy the coherence of the lasers. And this is possible, but it requires a strong effort. So to my understanding, there's only my colleague Jeffrey McCord at the Kiel University in Germany who is running such a microscope at the moment, using pulsed lasers. If you want to do lower speed, let's say power frequency dynamics for electrical steel, you don't need a laser. You can use LEDs as we do, and you can pulse the LEDs. Or you can also use high-speed cameras and pulse the cameras. So with power frequencies, this is much easier possible. But all this gigahertz dynamics requires a lot of effort. And it's, of course, it's only possible for repeatable processes. You cannot do single-shot imaging because you have to accumulate millions of equal events to get a significant or a sufficient signal-to-noise ratio.
Okay, I understand. Is there any other question? Okay, if not, I would like to thank Rudolf again for your beautiful talk. You're welcome to share with us your recent work whenever you want. So in the name of the lab, thank you again.
Thanks a lot, Luis.
Okay,
thank you very much.
Thank you very much.
It was a pleasure. So hopefully you can see us in person as soon as possible.
Yes.
Dean had a question, and Andres Rosales also had a question.
Oh, there's a question.
Yeah.
They're just clapping, so.
Oh, okay.
Okay.
Claudio, I don't know. Oh, they're clapping. Okay. Well, thank you very
Thanks a
much,
lot, everybody.
Yeah.
And
thanks, everybody, and see you next time, next week, for the next seminar. Okay, bye-bye.
Thank you. Bye-bye.
Bye-bye.